Okay, so so just to try to reinforce things that if you haven't absorbed them yet, hopefully you will. Um, so basically, you know, how what's going on with events and the scheduling? Um, well, the events, you know, by now you have each event corresponds to a do method. And the way that you schedule events is you make a call to wait delay. Now, what does that do under the hood? What it does is under the hood, it creates an event object. It's actually something called a sim event. And that puts it on the event list. Now, the event list is just a sorted set, the same sorted set that we used in the Java class, and the same sorted set that we've been using a bit in some of our models now. So it's the same Java object, and it simply sorts these sim event objects in the order in which they are scheduled. Okay, so now what happens when an event occurs? Now, what does that mean? You think all the way back to the beginning, the way that the event list works is you start with time 0, you look at the event list and see what is the earliest scheduled event. You move the the sim time to the time of that scheduled event, which could be a 0, it could be a 0 delay. And then at that point, the event quote occurs. So now what does it mean in SimKit terms for the event to occur? So the event list that is what's being called schedule, an unfortunately named class, but that is what it is. All it does is it takes this event object and it hands it back to the sim entity that scheduled it. Okay, so this is important to kind of understand. So because if you think about how you would write code that would execute these state transitions from a SimKit perspective that don't exist. Like, in other words, going all the way back to the arrival process, all that stuff in the arrival process class does not exist in SimKit itself. And SimKit itself has no way of knowing what it is that you, the modeler, intend. But it doesn't care about that. What it assumes is that, well, if you know what you're doing, and at least for myself, that can be not the greatest assumption in the world. But what it does is that sim event object has all of the information that the scheduling object needs to execute it. So now what is that? The main thing consists of the name of the event and any parameters if present. Those are the two key things. So when it hands it back to the sim entity that scheduled it, what the sim entity does is it takes it has a method. Again, this is not magic. It has a method. The method is called process sim event. And what it does is it says, okay, I see that I just got an event back from the event list. And this is its name. And these are parameters, if any. So and this is in the base class, in the sim entity base class that we all extend. What it does is it says, okay, do I have a method that starts with the word do, followed by the same name as this event? If it does, then it executes it. If it doesn't, then it just says, okay, you know, I don't care. So what does it take to execute it? Well, state transitions, those are defined in the do method. Canceled events, if there are any, we've seen a couple of examples of that. The canceled event calls interrupt, and then scheduled events, if any. So as a method, a do method need not have any of those, and it can have some or all. So we've seen examples of a do method corresponding to an event that has state transitions but doesn't schedule any events. One example of that was the part complete event in the transfer line that you just did. So that was an event. It had a state transition, but it didn't schedule any other events. There are other events that may schedule events but not have a state transition. Most events have both a state transition and schedule events. And we've seen a couple examples of canceling events, especially with that Renegade model, where the idea was that the Renegade event was scheduled when the customer arrived, but then when they started service, they canceled that event. Okay, so that was an example. So these are the only three things that go on inside of the event, inside of the do method. And again, the event list has no idea what any of that is about. So all the event list is concerned with is that when it decides that, okay, now I'm going to process this event, it hands it back to the SIM entity, and then the SIM entity that had scheduled it does its thing. And when all that's done, then the event list moves on to the next. It says, okay, is there a next event? Okay, so that how are events? Okay, now just one thing which I didn't list here is that what if the SIM entity does not have the matching do method? Well, then there's nothing to execute. And so the way that SIM entity base is written, the idea is that if that SIM entity base subclass gets an event and it doesn't have anything matching, then because it may hear that from somebody else and not care about it, that's not an error. So in other words, if it has the matching do method, it executes it, but if it doesn't, it doesn't execute it. And by matching, the key thing to understand there is that matching means having the same name and argument. In other words, this SIM event comes with a list of parameters or an empty list. So what SIM entity base does, it says, do I have a method that starts with do that matches the event name and has an argument list that matches this parameter list? And if it does, it executes it. If it doesn't, then it doesn't execute it. So for example, we've seen examples where there's an arrival event with no arguments and an arrival event with, let's say, a part argument. We saw that in the transfer line. So the transfer line component had an arrival event that had a part as its argument. Now, when it's listening to that part arrival process, it hears both the arrival events with no argument and the arrival event with an argument. The difference is when it hears the arrival event with no argument, it does nothing because it doesn't have an arrival event with no arguments. But when it hears the arrival event with the part argument, it does execute its arrival event with the part argument because that's the match. Okay, so now one of the consequences of that is that when you're debugging one of these models, you will sometimes see events being scheduled and actually seemingly occurring on the event list and nothing happening. When that happens, it's almost always a mismatch between the arguments or a fat finger on the name of the event. In other words, and it is case sensitive. So if for some reason I schedule an arrival event with a small a, even if the arguments match, because do arrival would be written with a capital A typically, then there would not be a match. Okay, so events are canceled. Now this is a little bit subtle because and a canceling event, when you cancel an event, it's a call to interrupt, and the signature of interrupt is string. It always requires a string, and what that is that's the name of the event that you're trying to cancel. And then if you remember what these three dots are, see these three dots here? These three dots are what Java called varargs. And what that means is that this second argument is either a list of things or it can be completely empty. So if I want to interrupt an event that has no arguments, then I would just simply interrupt the name. Now, what we saw at least in the transfer line, remember that the argument that was passed as the second argument was the customer, and that matched that was canceling the renege event of that customer. Now, the matching for this, and it, again, this was kind of implied or by the transfer line model, but maybe not as explicit as could be. So what it does is an interrupt call it will cancel at most one event. It will either cancel one or none. It looks for the first scheduled occurrence of a previously scheduled event for which two things happen. The name of the event has to match. And then, this is critical, the value of the arguments have to match exactly. So what was happening with the renege model, the name of the event that was being canceled was called renege. Okay, that should have been straightforward. The value of the argument, though, was that actual customer. And see, at any point in time, there would be a lot of different renege events. Like if you had 5 customers in the queue, there would be 5 renege events on the event list. And each one would have an argument of that customer who was reneging. That's why at the arrival event, it was scheduling the renege event, but passing that customer. So that when you pop that customer off the queue at the start service event, that was the argument that was passed to the interrupt of the renege. And so it would remove the renege event, not just the first renege event, it would remove actually the one and only renege event that had that customer as the argument. So this is for doing canceling, this is kind of a key thing. So it's the value of the arguments that have to match exactly. Okay, so now the thing is that with only this mechanism, you can actually create pretty much any model that's out there, and every model can be created using only this. But here's what tends to happen, is that if you're building a complex model, what tends to happen is you get more and more events that start, so that your event graph starts looking like spaghetti. And in looking at that, what you often can identify is the fact that most of the events are interacting, like you have these clumps of events that are kind of interacting with each other, and maybe only like one scheduling edge between one clump of events and another clump of events. At least that's what kind of was being noticed. And that was the motivation behind the idea of this sim event listening. So, and again, you've used this in a number of different models, but what I want to do here is we're peeling back the hood a little bit on what is going on with this sim event listening, I think. So remember that the event list, when the event list sees an event, a sim event, and it says, okay, it's now your turn, takes it off the event list, passes it back to the scheduling object, which then executes it if it can. Now, whether it can or can't, it then dispatches that event to all of the sim event listeners who are listening in. In other words, even if I have a component that doesn't have the event that it just heard from, that it just got back from the event list, it will still just try to dispatch that to any sim event listeners, because it may be that that event was just something that people wanted to hear from this component, and not, not people, but the other components. Okay, so again, regardless of whether it executes, it actually has a do method. That same sim event gets dispatched to all of the sim event listeners. And each listener, in turn, processes the event as if it had scheduled it. And the only exception is that if a component hears an event, then it doesn't dispatch it back to its listeners. So in other words, if it hears an event, it will process it, but it stops there. And that's what's been going on since there was this simple server. And that's what happened with the arrival event, and the arrival process would trigger the arrival event in the simple server. So what was happening there? Well, the arrival process was scheduling the sequence of arrival events. So when an arrival event occurred, the event list would pass it back to the arrival process. The arrival process would then do its thing, schedule the next arrival, and updated the count of the number of arrivals, and then it would dispatch it to its listener. So in that particular case, its listener was the simple server. And then the simple server would hear the same sim event and use exactly the same logic as it had before. It said, okay, I get this event. Now, do I have a do method that matches this event? If it does, then I'll execute it. If it doesn't, then it just stops there. So in the transfer line model, it was the same thing. When the arrival event with no arguments occurred in the part arrival process, the event list passed that arrival event back to the part arrival process, which then would, again, schedule the next arrival with no arguments and then update the count. And it would then instantiate a part and schedule an arrival event with a part. So then typically the next event to occur would be an arrival event with that part. So now here's what would happen is that when that wait delay in the arrival event with no arguments occurred, it scheduled arrival with a part argument. And all that did was create a sim event, put that on the event list to schedule at whatever time. Since the delay was 0, it would typically go to the front of the line. So then it would get that arrival event with the part handed right back to it. And then it would say, okay, well, actually in that case, there was no state transition and it actually didn't do anything. But then it would dispatch it to its listener, to all of its listeners. In this case, it was just the transfer line component that was listening, and then the arrival with the part would then be heard. Okay, the second type of listening is the property change listening, and this is the important thing to understand about property change events is that their only purpose is to notify anybody who's interested, any other object that might have interest in this, that there has been a state transition. That is its only purpose. A property change event does not cause a state transition. It reports a state transition. And so whenever there is a state transition, a property change event, and this includes index property change events, if appropriate, should be fired. Fired meaning you invoke fire property change event or fire index property change event. And again, this does not cause any change to the state. It just notifies, again, any registered property change listeners that that state change has occurred and what the values are. So the really one of the simplest and actually useful example of a property change listener is the simple property dumper. And all it does is whenever it hears a property change, including an index property change, it'll just print to the console, basically using a print line. This property changed from this value to that value. And one thing under the hood is that you notice that sometimes a property change event is fired with no old value. And the simple property dumper notices that when the old value is null, it just ignores it. It just says, okay, this is just the new value. It only reports the new value. This is useful for debugging. In production mode, I mean, if I'm going to run my model for 100,000 time units, I'm just going to get a whole load of spam on the output. So that's why in production mode, you turn it off, and you turn it off just by commenting out the listener. Now, here's what this fixes. This fixes the tendency to use a print line as a debugging tool. Now, this is one of my rant prep. Using print lines is the worst way to try to do debugging for a variety of reasons. What is useful about this is that it is non-invasive. In other words, if every state transition fires a property change and nobody's listening, then nothing happens. And that's actually a very, if there are no property change listeners and a fire property change occurs, it really doesn't take very much time at all. So what this allows is debugging without invasiveness. So in other words, if you're developing a model and you think it's working, and I want to do a production run, so then I comment out the property change listener. I run it for hundreds of thousands of time units, and then I look at my output, and maybe my output doesn't look right. Maybe I run it for 100,000 time units, and my average delay in queue is 0. Now, I mean, that sort of could happen, but is unlikely in most of the models that we look at. So that means that something is off a little bit. So I need to go back to debugging mode. If I was using, so with this, all I need to do is typically run in verbose mode. So switch the event list from verbose false to verbose true, and then just turn uncomment where the simple property dumper is listening for that component. And then I run a shorter run and I examine every state transition and every event and see where the problem is. Okay, so that's the debugging is the main one important use of this property change listener. And the reason that's that's so useful is that, remember that only state variables are the only thing that change value in one of these discrete event models. Only state variables. Parameters don't change. And so there's no point in listening for a parameter because it's not going to change. If I have 5 servers in my simple server, I'm always going to get 5. Now, for the parameters, the check is when you print out that object at the beginning, as we've been doing, and then you check the parameters to see, okay, if I expect 5 servers, I look to see that the total number of servers in that print line is 5. And if it's not 5, then I go back and fix it until it has the 5. But that's not the state. Those are the parameters. Okay, the main other, the workhorse use of this are these stats classes. These stats classes are property change listeners. Oops. And they work by adding new observations as they are heard. So if you remember the stat calculator that we did back in Java had a like new observation or something like that. That's sort of how these work, except that they respond to these property change events. So when a stat object hears a property change event, it unpacks it, it looks at the new observation, and then it will update its counters, kind of basically the way that you were doing it back then. The difference is that when we instantiated one of these stats classes, they had a name, and that name had to match what the state that was being fired. So each stat class only can respond to one state. And we've seen that there are 2 of them. There are tallies. The tally ones do things in the normal way, adding them up, divide by the number, as we've done. But then these time varying ones, and one of the things I hope you take from this is the idea of these time varying values. And they compute the statistics using the area under the curve. And under the hood, the time varying stats do that. Exactly how they do that is not something that you're responsible for, but if you're interested in how they do that and the exact algorithm they use, that's in the reading. Now, the one thing that's not, it's not listed here. The other one that we had are for both tally and time varying. They're the collection, there's a collection time varying one that we use to collect the time varying size. And then there are the multi ones, the multiple simple stats tally, multiple simple stats time varying, and multiple collection size time varying. What they do is they listen for index property change events and then sort out under the hood what they do. For example, the multiple simple stats time varying keeps a map of simple stats time varying objects keyed by the index. So every time it hears an index, if it doesn't have one of these time varying guys, it adds them, it instantiates it, adds it, and then updates it. And every time it hears another one, it will say, okay, I heard an index property change event for this with this index. Do I have a corresponding one? And then if so, I will update it. If not, I'll create one. Okay, so how do we start the simulation? We had the schedule reset. And one thing that you might have been wondering about is we had to write all these reset methods on all of our sim entities. And what did reset do? Reset initialized all of our state variables in that component, but you never called it. So how did that work? Well, what does schedule reset do? First it sets sim time to 0. And then what it does is it finds all of the sim entities that have been instantiated, and it invokes reset on those. So basically, schedule reset is like one giant reset button that resets everything. It does not reset the stats, though, and that's going to come up in a couple weeks when we start doing more valid statistics on these things. Okay, and then after it invokes reset, then it schedules, this should be an S, schedules the run event at time 0 with the highest priority for all components that have a do run method. So not every component has a do run method, but what it does is while it's sort of looking for this reset thing, it says, okay, do you have a do run method? If you do, then I'm going to put a run event on the event list at time 0, and I'm going to give it the highest priority. And the reason for that is to make sure that all of the run events for every component get executed before any other non-run event. And then after reset, we say start simulation, and that's what starts the event list algorithm, the event list processing. And what that does is it continues to invoke each event that is move sim time to that event, hand it back to its scheduling object, and it keeps doing that until the event list is empty.
Arnie, with that,
yeah, question.
Yeah, with that, so that's what you have to put the init in the reset, if I remember correctly. I'm trying to remember what's on man.
No, well, yeah, for the
nothing in SimKit that initializes.
Yeah, for array state variables, the idea is that well, for array state variables, we have that init thing that you're referring to, and so that's the way that array state variables are initialized with the run thing. But SimKit itself does not have that built in. You have to explicitly do that. Just as SimKit actually, the sim entity base does not have the do run method. It has the reset method. So reset is always guaranteed to be called on by the event list, but it does not have the do run. And so if you don't have a do run event, then it doesn't call it. Likewise, it doesn't have the init event. So if you want to initialize your array state variables, they have to be done explicitly. Okay, does that answer the question?
Yes, thank you.
Okay, yeah. So the thing is that there's kind of a tension between, and this is true of every application. There are competing principles for how much the application does for you and how much the application relies on the user to do. So for example, look at an application like Microsoft Word. Okay, when you create a new document, I think it, depending on exactly how it's configured, typically it will put you, if you just start typing, it will be in the normal style. But if I want to create, say the first thing I might want is a heading. So if I want a heading, then I, the user, have to explicitly tell Word, I want this text to be in a heading style. And if I want to do a bulleted list, I have to tell Word, this is going to be a bulleted list. Okay, now why am I saying all that? Well, when you're writing a simulation model, a discrete event simulation model, there are certain things that can be done regardless. One of those things is what the event list does. The event list can take events and kind of execute them, because what does it take? It takes a sorted set with these sim event objects, and it takes a loop that says, as long as the event list is not empty, advance time to the next scheduled event, pull that event off, send it back to to whoever scheduled it, and then wait till that comes back, and then keep doing the same thing again and again. But what is not reasonable is to have the application like SimKit have all the possible state, events and states and things in there. Just like it's not reasonable to expect Microsoft Word to already have all the text in your paper in it. It provides the mechanism for you to input that. So that's the tension between what an application can provide and what the user needs to provide. So basically, again, start simulation is what kicks the whole thing off. It just keeps going until the event list is empty. Now, the thing to understand there is that we've seen that there are 3 ways that this can happen. One is you can just run out of events. And as we've seen, like when we were doing things like just developing that for loop or the init stuff, if that's all we have, then we're going to eventually run out of events. And so the event list just naturally is going to empty. The second way that we've seen from the beginning is we said stop at time. We stop at this particular time. And what you will hopefully have noticed is that what that did was that put an event called stop on the event list. And that stop is that's one of the few built-in events in SimKit. And what the stop event does is when the stop event occurs, it simply clears out the event list. It actually invokes clear on the sorted set. And then when the event list goes to try to process the things again, it says, hey, now the event list is empty, we're done. The third way that we've seen a couple times is the stop on event. And that says stop after this many events have occurred. So under the hood, what SimKit is also doing is as the events are occurring, it's kind of counting them, it's keeping track of them. And in the verbose output, you can actually see that as every event occurs, at the very right, there's in a square bracket, there's a number. And that number is the number of times that event has occurred according to the event list. So the stop on event works when the right number have occurred, then it clears the event list and says we're done. Okay, so the ending criteria is always the event list being empty. Okay, so these are how we stop it. So the stop at a particular time. That's scheduled that special stop event, and which simply clears the event list. And then the stop on event, which we're again only requires 2 arguments and some optional ones. The integer is the number, the string is the name of the event, and then these are classes, which are the signature. So if I have an event that has a signature int, then that class actually has to be the object wrapper, that is integer.class. And it stops after a certain number of events whose given signature matches the vararg. So this is what's different here, and this is why I kind of emphasize the value thing on the interrupt. In interrupt, it matches the object. For this, it matches the class. So in other words, if I say stop after 10 renege events with a customer class, then it will stop after that many. I can't, there's no way for me to tell it stop after customer number 30 reneges. There just isn't a way of doing that. Okay, so how to debug these things? Well, first, verbose mode. What that does is that outputs the event list and the current simulation after each time. And so if the event list is running with verbose set to be true, it prints the sim time, the current event, and the event list after each event. And what's important for that is that you need to know when you're looking at it for each event, you say, okay, what are the state transitions? And there you look to the simple property dumper. And I look to what events are being scheduled. So if the state is in a certain value, and if that's the case, I expect to see an event being scheduled, and it's not, that means that there's a problem. And that's how I can try to figure this out. Now, one useful thing that we haven't completely explored and may not have a chance to go too deeply into, but this sim event listener idea is actually is a very powerful one. And what we can do is we can use it to build these lightweight components that add functionality without having to edit existing components. And here's an example. Remember our original simple server component. One of the problems that we had with that was that because its states were the number in the queue and the number of available servers, we could not explicitly compute the delays in the queue. We couldn't explicitly compute those. We could infer them through Little's formula. But if we wanted to, kind of a lighter weight way of confirming Little's formula would be to define a new component, again, just with a first in, first out Q of these entities. We could create these entities of the arriving customers. And then what we could do is we could listen to both the arrival process and to the server component for a start service event. Here's what that looks like. Okay, so here's our original arrival process. And here's our original simple server. Again, I haven't put the state transitions in there, but again, all we had was Q and S. So there was no way with just these two that we could explicitly compute the delay in the queue. Okay, but look at this. So now in this component, we have a state variable Q, which is initially empty. So all we need are these three events, and they're not scheduling anything, they're just listening. So this will hear an arrival event from the arrival process. And when it does, we simply add a new entity to our queue here. It will not hear, and this is important to understand, it will not hear this arrival event. And why? Because this arrival event in the simple server is heard from the arrival process, and so it does not get dispatched to its listener. But it will dispatch start service and actually end service for that matter. But what I can do is I can at least do the delay in the queue, keep doing this, by when it hears a start service, it pops off the entity that it put in here and then gets the elapsed time. Don't know why this keeps doing this. Okay, so now again with just a very, very small component, I now can extend the functionality by I can now do something that my original model could not.